I personally have so much excitement because as a doctor, I see patients, I read a lot of their history and things to understand what's happening, but also so much of that data is encoded in images, right? Every day I'm looking at x-rays of the chest, CT of the head, looking for, tumors or bleeding. I'm also reading heart traces, ECGs or EEGs, brain traces. So if we could combine these modalities, the potentials are enormous. Hello and welcome to Dev and Doc. This is a podcast where developers and doctors join forces to deep dive into topics of AI in healthcare. My name's Josh. I am a doctor and an AI clinical researcher. I am your co-host, and with me today is...
Željko, and I'm the developer.
Today we're going to be talking about a super exciting topic which everyone is talking about, and that is the new release of the public multimodal model by OpenAI, GPT-4. So we're going to be deep diving into this multimodal universe.
Yeah, there has in fact been quite a bit of news in the past 2 weeks with multimodal models. Not just OpenAI, I think there is a lot of movement on the open source side. People are building multimodal models on top of Llama. It is in fact called Lava. I in fact forgot why, but it's just an abbreviation of everything else, like always. There has been many other models also, what public, what private. We had, I know, some research from Alibaba where they were releasing their own model, a large language model, and then a bit later also a multimodal model. There was also some research from a couple of other companies like Adapt, who released their own model. So there was like 5 big papers and big models that were released only in the last like week or two for multimodality. But maybe before we go into this, do we want to just address a bit what is multimodality and why is everyone doing it? Why is it important?
Yeah, so in the general perspective, we've been talking so much about large language models that take in text and can output text. And we've talked about all the incredible things it could do in the previous episodes. Now, the one thing it's missing is vision. Because as humans and also as doctors and clinicians, so much of our data is in images, right? I mean, you can see it in social media. You scroll through Instagram, it's all photos. If you read a book, it's text. So it's a way of combining these two modalities that we use so much of and really just drawing that power together to deliver as much impact as possible. I personally have so much excitement because as a doctor, I see patients, I read a lot of their history and things to understand what's happening, but also so much of that data is encoded in images, right? Every day I'm looking at x-rays of the chest, CT of the head, looking for, tumors or bleeding. I'm also reading heart traces, ECGs or EEGs, brain traces. So if we could combine these modalities, the potentials are enormous.
Yeah, and combining here, I mean, vision is not something new, of course. Model that can detect, that can work with chest x-rays is nothing new. But what is exciting here is that now you can, in text, basically in free text, ask the model about something in the image. So it is not like made to do one specific task, but you can upload any image you want, an image of your cat, and you can ask, oh, what's my cat doing in this image? Or what's the color of my cat? Or where is it going? Or anything like that. So not just on the medical side, but you can also imagine for people that are hard of seeing or completely blind people, these can help them a lot because they can upload images and have something that will tell them anything they want about the image. They can basically have a conversation with an image, something that will explain them and where they can ask any questions. And I even think this was one of the initial use cases of GPT-4V, the OpenAI model.
Yeah, exactly. It was made for a trial for visually impaired people. So you could essentially take a photo of something, particularly if you're if your eyesight, especially kind of close distance, is poor and you can't read, so you can take a picture of menus, take a picture of items in the store, and GPT-4 could explain to you what was in your hand. So that was very powerful.
I did try it with handwritten stuff and it was working. What was usually a bit necessary is to provide a bit of context. If it's like a word that is a bit strange or that, I don't know, is not used frequently. If you provide a bit of context, or if the written note is a bit longer, it was usually working very well. The problems that I've noticed myself is that if the handwritten stuff is very long, so if you are writing, I don't know, really a full-on A4 page, then it gets messy. Then it's like it doesn't even follow rows properly. Sometimes it can skip a row. Sometimes, I don't know, it includes additional information that are not there and so on. So I think it is still very nice, but maybe more for shorter stuff. It should not be like really used for OCR. Its purpose currently is just recognize snippets of text that are here and there on a page or something like that.
I mean, the big thing is the versatility, right? You can do OCR, you can do arithmetic, you can count apples, and I've been testing it qualitatively in different medical domains. It can look at pathology reports, it can look at radiology reports, it can look at ECGs. This is something we've all been waiting for as doctors, especially if you can interact with it through text. It makes it so easy. Just imagine if a patient came in and you had a closed source kind of LLM and there's no problems of privacy. You could essentially, alongside as you see the patient, you can tell the model what's going on. They can read your notes and they could look at the images and contextualize everything. And it could suggest diagnosis. It could point out the abnormalities. We know in the previous episode, we talked about super doctors. We know that when the doctor is combined with an AI, their performance improves significantly. So this is very powerful, and the future there is just amazing. I think, should we actually dive into some of the cases and papers that have been looking into the medical capabilities of GPT-4V? This is the most interesting paper, which is the Microsoft published paper called The Dawn of Large Multimodal Models, a preliminary examination of GPT-4 vision. And this is very exciting stuff. So you can see here, they've basically talked about how this generalist multimodal model has encapsulated a lot of important medical knowledge. And it's given some examples, and importantly, it said that this is a great opportunity for radiology reporting. So the first example here that we have is a abdominal film, a very common X-ray that's done in the emergency department for patients with abdominal pain. And the prompt is write a radiology report for this image as an expert radiologist. And you can see here, GPT-4V produced a perfect radiology report with the date, with the exam, with the history and indication, and a nice conclusion. And it detected the positive finding, which was suggestive of a partial small bowel obstruction. This is a very important emergency for doctors to pick up, so it's very promising that GPT-4V has picked this up and reported it appropriately. Another example here is a wrist X-ray. So here the prompt is write a radiology report for an expert radiologist following this case. And the case is a 32-year-old woman falling on her right wrist, complaining of pain while she was playing basketball. And once again, GPT-4V does not fail. It's produced a perfect report of the X-ray of the right wrist, and it's identified the transverse fracture of the distal radius. Now, this has big implications, right? Because working as an emergency doctor, it's very time pressured, and there's a lot of people coming in for falls, and sometimes there are fractures that are minute and that are sometimes missed, and we don't often have time to wait for a radiologist to report these scans because the volume is so high. So if GPT-4V can detect fractures in the emergency department, that is a very, very useful tool. And the next example is incredible. It's basically fed GPT-4v a series of chest x-rays. So it's saying that this is a chest x-ray from the previous admission, and this is an x-ray from the next admission, and there's two scenarios. So one is the patient has pleural effusions, so fluid in the chest, and in one instance it's gotten better, and in the other instance it's worsened. And GPT-4v was able to basically write a comprehensive report with reference to the first scan. So here you can say there's a significant improvement in the patient's condition compared to previous, and then the other one that says there is significant worsening of the patient's pleural effusion, both correct. This is really incredible.
Yeah, I think you linked the very good paper from case studies, I think from a university in China.
Yeah, so this is a lab from China, and essentially they explored what GPT-4 vision can do in the realm of medicine, and they identified two of the main topics, which is in radiology analysis and also pathology analysis, so looking at different slides. Maybe first we just delve into radiology, because I think that's the use case that everyone's the most excited about. So what I could do is, across all the different domains, different organ systems, so the head, the foot, the abdomen, it can identify all kinds of things, right? So in chest x-rays, it could identify pneumonias, it could identify fluid from cardiac overload. In brains, it could detect tumors, bleeds, all kinds of things. In bones, it could detect fractures. So there's a lot of promise here. All they did was basically feed this image to the model and asked, what's there? What's the abnormality? And they showed that it could do even better if you gave it a bit of a clinical vignette, so a bit of a history about what the patients have come in with. And that has been shown to improve the performance, which is not surprising.
I mean, that sounds very interesting. Do you maybe want to show a couple of examples?
Okay, so this is a nice example. So they've fed GPT essentially an image of a brain tumor, an MRI scan, and they've asked, what could this be? What is the diagnosis of these brain MRIs? And you can see here that the model has correctly identified that there is a mass, that they've correctly identified that it's a brain scan, and they can say there are these abnormal areas of hyper-intense regions with some cystic components, which is completely correct if you look at these images. So it's very good. It's without any, prior prompting or patient history. It's managed to identify that there is a mass there. And, it's also given other differentials. So, for example, it says it could be an abscess or it could be other space-occupying lesions. So that's a very nice use case. And just let me find another one. Okay, so this is another case. This is a cardiac case of a pediatric patient. And essentially there are some, you could say, possibly subtle changes on the chest x-ray in keeping with cardiac failure. So the heart's a bit bigger than normal. And the pulmonary vessels have shown something called engorgement. So it's basically backup of pressure. Signifying possible heart failure. Now, GPT-4 Vision has looked at this and said, oh, there's no pneumonias, there's no obvious masses, which is correct. But it's also said, oh, the cardiac contours are within normal limits, which is not technically correct. So, there are some shortcomings. I think from this qualitative reports, it might suggest that it can identify things which are quite clear, like big consolidations, but if there's subtle changes, it may not pick it up.
I think I think it is even, to me, it is even a bit surprising that it works for these things. I think it was mostly, again, we don't really know what the model was trained on, but it is probably mostly images from the internet. So the fact that it works for these cases, it shows possibilities. It just shows that what will be possible once the model is properly, completely trained on really X-rays and CT scans and whatever else you can imagine from the medical domain.
Yes, exactly. I mean, keep in mind this is still very early days. If this was a drug, this would be like, lab studies slash preclinical studies. So it's still very early days, and there's still many different works that need to be done to improve these models, but it demonstrates the massive potential it has.
No, exactly. Yeah. It is just showing what can be done. And I think there are, of course, many more examples here from the medical domain. And I think all of these examples are a bit cherry-picked, but it is there to show exemplars, to show, okay, this is how things can work, or this is what can be done. I do know like there are people who basically on paper drew a website, like, oh, I want my website to look like this with a button here and with a logo here and whatever else, and then went into GPT and said like, oh, took a picture of that and said, oh, code me that in HTML. So HTML is used to build websites, and basically the model, so GPT will write the HTML and you can just copy paste it and have a website ready. Again, it is showcasing what is possible. So there is a million of these use cases, and you can just imagine you just have a model that you can take a picture of whatever you want and give it a task to do that, and it will try its best to perform it.
Okay, so let me talk about the second part, Jauko, as well, which is pathology. So in the paper, they looked at 20 different pathology slides. So, these are normally kind of, tissue samples or blood samples taken from patients and put in a slide, and they look through it in a microscope. And they fed it 20 different slides. And the good thing is that GPT was very good at identifying what was the stain and what was the common kind of general tissue features. So clearly something it's picked up in its training from the internet or textbooks has taught it that, okay, if it looks like this color and it's this kind of cell, it's likely to be this kind of structure. So that's really promising. But where it falls down is actually coming to a solid conclusion or diagnosis. So in those 20 cases, we saw that GPT-4 vision misdiagnosed 4 of those cases as normal when there were abnormalities. It correctly diagnosed only 3 of those 20 cases. And the other 13, it basically refused to go into any concrete diagnosis. It just gave a vague answer. And we're seeing this more and more, as large language models and large multimodals are released, OpenAI and other companies start putting on safety rails around it. And what that means is it will start refusing to say certain things, because you could see people were initially abusing some of these features, asking it how to make bombs or how to make dangerous chemicals. So because of those safety rails, sometimes it refuses to give a medical diagnosis, knowing that this could be dangerous if a patient was using it. So that's some of the shortcomings. But I think, Jauko, did you want to dive into some of the other models available at the moment?
Yeah, for sure. I think there are many more interesting models, and in fact, I prefer the open source models over the stuff that is released by OpenAI. There are, in fact, I just want to touch a bit on the technical side, just to say that there are in general 2 different approaches that are used for building these models. So on one side, what is done is that you have your large language model. So you have the model that works with text, and that's one transformer model. And what is done in one approach is that next to that, you build another transformer model that is a vision transformer.
Yep.
And then you basically combine those 2 models. And then you end up with a multimodal model. So you are basically combining 2 models, a vision one that is already trained on vision tasks. So that can be classification of images, recognizing of objects in images, whatever else you can think of. And then you combine those 2 models and end up with one big one that can now handle both text and images.
Yeah, that's really interesting. and we've talked about transformers in the previous episode. So you're saying that basically there's two different transformers side by side, one for the language and one for images. Is that right?
Yes, in fact, they are not really side by side, but the image transformer is feeding into the language transformer. So, and then it is allowing the language transformer to understand a bit the images and also to get other text as input.
My initial understanding was that you don't really need two transformers. I thought one was enough, as long as you can change images into their token representation, which is, you know, a readable format from the computer. Do you need a vision transformer on the side or on top?
So in fact, you don't, and that is the second approach. So there are two major approaches. One is this one where you have a vision transformer and a language model, so a language transformer. And the other one is where you have only one transformer and you are feeding text or images into that. So you're basically feeding whatever you want. How it works is that you basically split your image into patches, like into a grid, I don't know, a 4x4 grid, and then each one of those small boxes, each one of those patches becomes a token that is then fed into the transformer. So a token can be a patch from that image, or a token can be a word. And in that way, now you have one transformer that is doing everything. But what is the difference is that in this case, that one transformer has to learn everything. Yep. So that one transformer has to learn everything about images and everything about text, somehow separate that knowledge inside of it and keep all of it in that one transformer network. Network here meaning like a neural network.
Yeah, but if I look...
Yeah.
Sorry, but if I look at an orange... and if I read the word orange, my brain would still think of the idea of the fruit's orange. So would it not make more sense to have one transformer and you feed both inputs into it like that?
No, that's a very good analogy. And in fact, what this other vision transformer is acting as, or how I would see that, it is acting as eyes. While in this first version, you would basically be feeding the image directly into the brain. No eyes as the intermediate. Basically, no something that can perceive and a bit format the input, but it is going directly into the brain. So,
yeah. So have they tested these two approaches? Which one actually does better in what kind of instance?
To be honest, it is very hard to say. They have, of course, tested this. Why is it hard to say? Is because when a new model comes out, it is usually better than everything else. And then tomorrow a new one will come out and then that one is better than everything else. So it really just depends what is the most recent transformer that came out. In general, the combined approach, vision plus language, so not the combined, the one that uses two transformers is usually better.
Interesting.
Just because you have a bit more training data, you have already existing big vision models that you have trained for, I don't know how many images and on how much data. So I think there was not too much exploration done on these models that take everything at once. Those ones are a bit more popular just because they are easier to make. It's much easier to train something separately for vision and then something separately for language and then just combine them, because usually it can be even the different groups have done that. So if you remember OpenAI, how they have done this with GPT-4v is that they've used one of the previous models they have made, which is based on like the PaLI-3 and Clip architectures, which were basically models that can either generate images or classify images or do stuff with images. And they just had that model, combined it and fine-tuned a bit further and ended up with GPT-4v.
Interesting.
a very similar thing is done with this Lava model. So Lava is based on Llama. And what they have done is they took an open source clip model, which is a vision model. They just found some data that is combining an image and text. I'm saying like they just found some data. It's not some data. They found a lot of data, and it's a lot of processing. It's a lot of combination. And they even used other models to create synthetic data and so on. But in the end, they ended up with a Lava model that is basically a combination.
So this data set is basically describing images, right? So you have one side is like, oh, this is a picture of a cat, and then the text paired data is this is an image of a cat sitting on a stove, whatever.
You have everything you can imagine there. It can also be, like you said, a menu and the text describing everything that is in this menu, or really a full-on conversation, like a menu and then someone asking what's the cheapest item, and then someone answering, and then someone asking further, and so on. So it is basically conversations around images, either labels on images or conversations or anything else you can imagine with images, basically.
This reminds me almost of instruction tuning data sets for large language models, but for vision. So we talked in the previous episode where you have data sets where you have a question and an answer pair that you can train the large language model on. Would you say this is kind of the equivalent, but for vision models?
Yeah, it is exactly that. Basically, it is. You are just
you need a lot of data, right? You need just imagining the amount of images out there and the descriptions. You'd need so much data, probably more than text data, no, to get a good performance.
Oh, in fact, if you are using this approach that is a vision transformer plus a language transformer, then no. Then you need a relatively small amount of data. Wow. Maybe you need 20, 30, 50,000 image text pairs. And you want them to be as diverse as possible. If you are training the model from the ground up, like the one from Adept, the one that they've released is called Fuyu. And that one would need a lot of data. In any type of data that has images and that has text, or images alone or text alone, because that model can take anything, and then you need a lot of data to bring it up to speed.
That's incredible. You know, I'm just imagining, we talked about using these models for the visually impaired. Imagine if you could get this, into the glasses, which, all the big tech companies are making, like Google Glasses or Apple Glasses. Imagine if you could have a live video feed telling you what's happening, and you have an earphone that's telling you exactly what's happening, or reading the menu. That would be really cool.
Yeah, I agree. That does become a bit dystopian, and I think can bring problems. Having something that is telling you everything about the world ever. But I agree that there are some very nice use cases that, I don't know, if you are somewhere and you don't know what's that in front of you, you can just point your phone and say like, oh, what's this? And it will take a picture. It will use a vision language model and tell you, oh, that's whatever, the cathedral that was built in 1500s and whatever else. So it is, it's just like a tour guide almost that's telling you whatever you want.
As long as it doesn't detract from your experience, right? Can you imagine if you're sightseeing and you're just on your phone, just taking pictures all the time, or talking to your glasses? Yeah, true.
It can get, we should not lose the human touch part where you are socializing with people and talking about what's that in front of you. But I think it has giant potential, basically.
You've highlighted those different models that have come up in the last few weeks. Are there any other models you wanted to cover?
Yeah, for sure. I think I just want to cover the big ones, or the ones that could become foundation models, meaning models on top of which we can build other things, and just to highlight different architectures and possibilities. So
should I just explain foundation models briefly for some of our audiences? So the idea is because we have all these big companies with lots of money and lots of compute, lots of different processors and GPUs, they're able to make models that are very powerful with many millions and billions of parameters, right? So the idea in the future is that these big models, because organizations like the NHS or smaller organizations, they can't train models to this size and this power. So what is most likely is going to happen is you'll have a big model from OpenAI, a big model from Microsoft, a big one from Amazon or Alibaba. And what people would do is take those big models and add another layer on, essentially to fine tune it to your use case. So we might take OpenAI's foundation GPT-4 model, and then we might fine tune it with some healthcare data so it's more useful in the NHS, in the healthcare setting.
Yeah, that's a very good definition of foundation models. It is basically a general model that can be specialized with very little effort. So creating that foundation model takes quite a bit of time. It doesn't have to, that's not the rule. A foundation model is simply something that is very general, that can do many, many things, maybe not on an expert level, but basically like a jack of all trades. And then if you want, you can take it into your organization, your hospital, whatever, and fine tune it on a very specific use case. Now, of course, it's also important to know that a lot of these companies are not releasing these models. Google's not doing that. OpenAI is not doing that. They allow you to fine tune the models. Like OpenAI has an API, so an interface you can use to fine tune your own version of ChatGPT. But you cannot take the model. You can upload the training data to their servers and fine tune it, but you cannot take the model to your organization. And as such, I prefer the open source models, which are basically these foundation models, but that companies or institutions or labs have released to the public, that anyone can take and use and do whatever they want with it. So one of the most popular ones is the Llama model, now Llama 2. That is in fact the only one that is, it is nearly open source, just because you have that one small limitation that if your organization has more than, I think, 500 million, no, or 500, was it 500 million users? Then it's not, then you cannot
then
use
it's not
it.
free.
Yeah, but for most of us, that means it's free.
But, you know, therein lies one of the big problems we've been talking about. Like, I know Stanford released a paper just last week as well, looking at a framework at evaluating model transparency. So how much do we know about these models? How are they trained? What data is used? What methods are used? And the best performing transparency model was Llama 2, like you said. But the score was only 54% out of the 100-point index. So, you know, there's almost half of the training that we don't know. So how can we use this in healthcare if we don't know what's gone into it? That's one of the big questions that will arise in the future, I believe. Like, how do we know this foundation model? Number one, how do we choose which foundation model to use? And number two, how do we know what's in the foundation model? Is it, you know, are there biases within it that we actually don't want in healthcare? How much fine tuning will it take to overcome that bias? These are big questions that I'd love to talk about in another episode. But yeah, why don't we talk about the other models that's come in the last few weeks, Jabko?
Yeah, so one of the important ones was from Google. Why is it important? It's called PaLI-3. Why is it important? There is a accompanying paper, but the model was not released to the public. Maybe it will be somehow, like in the paper, they made it seem that it possibly will be released. Why was it important? Because it's a relatively small model. This is also a multimodal model. And it's important because it only has, I think, like 5 billion parameters. But what's good is that it is working almost better than like 10x larger models. So
insane.
because of the architecture, because of the training data, this is fairly well covered in the paper. We saw that it is working well, very well. And there is in fact one interesting note for this model is that most of these vision models or multimodal models have a decoder only architecture, and what was important for this model is that it has an encoder decoder for the language model. So I don't want to go too much into this, but for example, models like GPT are decoder only, so you only have that decoder portion in the transformer, and models like BERT or similar were decoder encoder.
Yeah, we talked about large language models in another episode, but I think we need to do a deeper dive into these encoder decoder models at a later date.
Yeah, no, I agree for sure. I think we didn't cover really transformers in details, but yeah, this is just an interesting side note that most models are decoder only, and this one that is used here is an encoder decoder. So yeah, that's it basically.
So that's great. So you can run, essentially this Google model is very lightweight. And so theoretically then the argument is actually, can we actually create one and from scratch with this architecture without reliance on foundation models, right? Like can the NHS theoretically, if we have a couple more GPUs and some money to spare, can we just train the model from scratch and maybe not rely on these foundation models in the future?
The thing with, like, when you're saying not rely on foundation models, I think it would be very similar. We would just be creating our own foundation models.
Exactly.
So you would not be relying on someone else, but you will be able to do it yourself. Now, is that possible or not? That's a tricky question, because the fact that, sure, it is a slightly smaller model, it is 5 billion parameters, but it is still a bit too big to train it on a couple of GPUs, especially if you're looking to train it from the ground up. There is always a very big difference in I'm just fine-tuning the model, which usually can be done, like people are today doing that on your MacBook, like on a laptop, basically. You can fine-tune these 5 billion model or even a 10 billion model easily. But to train it from the ground up, you would need 10 years on your laptop.
Okay, yeah, so still still a problem to be solved in the future.
I mean, problem, again, hard to say. Is it a problem or no? It just means, like, are we relying on others to create those models? Because I think even if we manage to, even if we can create a 3 billion parameter model or a 500 million parameter model, I'm still fairly sure that the big one will be better. And I don't think this is like reliance. I think this is more collaboration.
Yeah, it's the transparency issue that we talked about. Can we use a model that's not transparent? You know, so you're using a black box within a black box. You know, a transformer model is a black box, and then the training and what they're using to train it is also a black box because the company won't release that detail. So, you know, can you use something like that in healthcare?
No, of course. I mean, that part is important. There you want the company to release the data. And there are companies who are releasing the data. There are companies who have released everything that the model was trained on, and then you know everything. I don't think in general that's helping you too much. Like, we are saying here, oh, for healthcare, it's important to know what it was trained on. But this was trained on like 3 to 5 trillion words. There is no way to screen that data set. There is no way to know was there anything there that is like harmful or not harmful. I think the only way to test that is basically experimental, not quantitative and qualitative tests later, which makes sense to some extent, I think, because the model is basically collecting all of internet and being trained on that. Sure, there'll be something there that's not the best ever, that should not be used, but what we hope is that the model will learn to ignore that.
Yeah. So there needs to be almost like a clinical trial of language models to see how it acts in clinical setting.
Yeah, of course. And as we were mentioning before, it really depends on the use case. If your use case is transcribing notes or clinical coding, maybe you don't need to go through a clinical trial to have it deployed. But if it will be diagnosing a patient, giving medication recommendations, maybe you need to be a bit more careful. And it is still is it used together with a doctor? Is it used by itself and so on? So I think there are many levels there, and a lot of them don't require that strict checking as clinical trials.
Yeah. You've covered all the models you wanted to cover?
Yeah, I think that's it. So if I just sum that up, so we had the GPT-4V by OpenAI, we had the Fuyu model by Adapt, we have the Lava, or in fact Llama, to some extent by Meta, to some extent by independent researchers. We have a model from Alibaba that is called QWen, and the PaLI-3 model from Google. So I think this is basically everything that came out in the last 2 weeks, which is unbelievable. It's 5 big models that all came out in the last 2 weeks.
The pace is just, I can't keep up with the papers. Every day there's 10 new papers to read nowadays.
Yeah, it is impossible. Sometimes I read someone talking about a paper and they say oh, this is a slightly older paper. And I look at the date and it's 5 days old. I was wow, what? Is 5 days now slightly older?
Yeah, it is. 1 week and everything changes. It's incredible.
Yeah, that's true.
Yeah. Look, we've talked about the promise of these multimodal models, but we just wanted to basically ground what we've said and talk about some of the shortcomings and perhaps work that still needs to be done. Because like I said, we're still very early. Let's be honest, we're still very early in this stage. And not just the healthcare sector, I think every sector is currently finding different use cases, new use cases for these models, ways to control them, ways to improve them. So this is going to be a cycle for the next months and years to come. We'll be fine-tuning these models better and better. They'll become more lightweight, perform better. But I wanted to talk about some of the findings in the paper we mentioned. So it's shown massive potential in pathology and radiology, but it's still making very simple mistakes. So we talked about how, in 20 different slides, it only correctly identified 3 abnormalities, and the rest is leaving, it's missed for diagnosis, and it doesn't really give a good answer. This gives a vague answer for 13 of the cases. And just very quickly, I wanted to touch upon why it's giving these vague answers, and I foresee this is going to be a problem. Because in an effort to control these models, we've talked about large language models and the shortcomings, and in many ways it mirrors that of large multimodal models as well. You can hallucinate, you can make mistakes, you can be overly confident, you can have biases and inconsistencies. And one way that these companies try to improve the model is by putting in safeguards. So for example, if someone's trying to do something harmful, they'll train the model to not give an answer. And likewise, they've done the same for the medical domain, because they're worried that people will use this model for health advice and take it verbatim. So that's why in many of these examples, it just won't nail down the diagnosis. So it might try and say, oh, I'm not qualified, you should seek a medical professional, or it might just suggest a few things which seem sensible. But this is a big problem. And Jelko, I'm not sure how to, how do we address the safety of a model without limiting its performance? I guess that's one of the biggest questions I had so far.
Yeah, I think there is for sure something in the model being limited and not giving an answer, even though it might know the answer. I think in most cases it is the model does not know the answer. I think even if there were no safeguards or anything, I don't think it would be able to answer many of these questions, just because I don't think it has ever seen that. Again, we are speculating here.
Yeah.
We are speculating, does the model not know, or is it simply being restricted? So it is hard to say what is the real reason here, but what's the basic conclusion is that it does not work for those cases. Irrelevant of the reason, it does not work for them. Now, about your question on how would you do it safely, or how would you implement these restrictions in the model without degrading the model itself? I think that's a hard question. And there are, I think, two main approaches that I saw people doing currently. One is teaching the model not to answer. So when someone asks a dangerous question, teach the model to not answer that. And I think that one possibly is degrading the model. But
That
again, this is not
degrading the model.
This
I mean,
definitely would require proof. We don't know. There was not a proper test. Like there was
we
no
don't know
one
how much it degrades by. But no, I did see a talk from one of the GPT-4 authors, and they openly said the release version is attenuated. It performs a lot poorer because of these safeguards. They openly said that it is a lot worse, and they showed some examples which may not be the best examples, but they asked it to draw certain things, or they asked it complicated questions. It could do that in the original model, but after these safeguards, it really couldn't do it very well.
I think, again, I did not see any proper tests on these. All of these things that are currently being done by many people are showcasing a couple of examples.
It's qualitative, that's the problem.
Yes, it's qualitative. And even all of these tests that we have seen today, it was very qualitative. It is, you look at 20 images and then decide something based on that. I mean, you would want one disease and maybe 1,000 examples for that. Like, I don't know, a chest x-ray, and there is one problem with that, and then 1,000 different examples, 1,000 different people, races, nationality, whatever else you can imagine, and then you can make some quantitative conclusions, I think. But it is obvious that these models still have many problems, and a lot of these will require proper studies and proper research papers that will address the performance in specific domains. But I just wanted to come back to the two different approaches. So the one approach was, as we just mentioned, where you are basically fine-tuning the model not to respond. So you're telling the model not to do it, which possibly, as also you said, could degrade the model. And the other one is you have a model that can do everything, and then you have another model on top. You have basically a sensor model that will jump in the moment the first model starts outputting something, or when it detects the user is asking something that is dangerous, or that the model should not respond, or if the model responds with something that is inappropriate. Which this way is obviously not degrading the model, because we are not touching it. But it is more expensive, it is more cumbersome, it's more complicated, just because you have a separate model that now has to do the censorship. I don't know which one's better.
Another thing that could, more research should be done to look into, I guess, to see which of these approaches yield the best results. I think that's the problem. I completely agree. I think as scientists, we really want, ideally, large scale, large numbers, real world results. And at the moment, unfortunately, all the promise is there, but it's all kind of qualitative, perhaps even cherry-picked examples. Yeah.
Yeah, but I think that's also fine. Everyone is still at the beginning. I mean, it is still strange to imagine that ChatGPT is not even a year old. And the amount of research that came out after that is unbelievable. So I think everyone is still trying to understand what is possible, and all of these papers are just showcases, are just maybe cherry-picked, maybe not, maybe just... It doesn't have to be cherry-picked, but also if you show only one example, it does not tell us anything. It tells us that this could be possible, or maybe you were lucky. So it tells that these models are capable, but we don't know still how much or what are all the things that will be possible.
Yeah, so I just wanted to touch on a few last points from the paper. And basically, in radiology, they found that the GPT model was very good at identifying the type of imaging and the body part that was being imaged, but the anatomy localization was particularly poor. So, obviously, in a scan, we want to know what the abnormality is, but also where is it? And it was getting a lot of things wrong, For example, the left or the right side, or like which anatomical structure, like in the lung, which lobe, the upper, the middle, or the lower lobe was affected. It kept getting these things wrong. And until that improves, it's going to be hard for it to be really useful. I did see a paper, we can link it in the description. I just remembered, but someone actually tested this kind of object and location awareness in GPT-4 vision. And one thing they did to improve it was to use a segmenter. So they run a segmenter on top of the image, which then basically numbers the different objects in the picture, and then they can ask GPT-4 vision, what number is the abnormality in. So in the example I saw, it was like a kitchen, and they're saying they've numbered all the mugs, the kettles, whatever household objects, and they said, okay, now tell me where the mug is, tell me where the toaster is, and it showed basically way better results than just giving it an image and asking it where the toaster was.
Yeah, I mean, that makes perfect sense, basically, just because I think the spatial reasoning and counting, the math side also, is not still the best, or localizing things, which some of these other models, like the one that I was mentioning that was from Adapt, they are saying that it is significantly better for localizing, or for finding things in images and finding the exact location, and even like telling you the bounding boxes of something. So basically, where exactly is it on the page? So some of these other models could be better. But again, as we mentioned earlier, not a lot of tests, very hard to determine. And a lot of papers I see today that are still coming out, which I think is also one of the problems. I think we had enough of showcase papers. There was this one that came out from, was it Microsoft?
Yeah.
The one that is like a 70, 80 page paper talking about GPT-4, where they are basically showing like 100 examples of where does it work.
Dawn of LMMs, Dawn of large multimodal models is the paper.
Yeah, and I saw like the first example. We can also show that on screen. The first example is like a picture with, I think, 11 apples in it. And the first example, or one of the first examples they're showing, is like, oh, if you ask the model how many apples there are, the model tells you immediately 12. So it makes a mistake. But then they go on and say like, but if you ask the model to specifically count the rows, and if you tell the model that it's an expert and blah, 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 and then you ask it how many apples are in the picture, it tells you 11. So it tells you properly. And then I went and tested that myself, and it's not true. I mean, occasionally occasionally it still tells me 11, occasionally it tells me 13, occasionally it's 12. So basically they gave again an example that doesn't have to be cherry picked but not properly validated. And if that is the first, because once they describe this first example they say, oh, and now we are basing everything on this. You made a mistake on the first one and you are saying I'm basing everything on this. To me, like we should at least improve the science a bit on the papers we are releasing. Scientific rigor on the papers we are releasing around these GPT stuff and other vision models and other large language models and all of that. I think we had now the year of everything is new and we are trying everything, but we should switch to go back to proper science and do things the way they should be done.
Yeah, agreed. Yeah, I completely agree. I mean, there's so much promise, and I think everyone wants to get a publication out of it, but we really should be encouraging more grounded, scientific, rigorous investigations. But yeah, look, in this episode we've covered a lot. We've covered the potentials. We've covered a bit about foundation models. You know, there is a lot of promise, and I can't help but to be super excited. And you know, not to end. I think we should end on a high note and just say that these models are very, very early on, and they've already shown so much promise. So let's see what we can do with it as doctors and developers. Let's see what we can make to see if we can make an impact with these models.
I completely agree. I think this is awesome, and the progress we are seeing is better than ever before. So the future is bright for sure. Yeah.
Okay, great. I think that kind of covers this episode. We've talked about a lot of interesting things, and I'm sure there's going to be a lot more to come. I will see you on the next one.
Thank you very much for listening. Subscribe and comment, and we'll see you in the next one. Bye-bye.
Yes. Bye.